Hi, my name is Melanie Escobar, and in this video, I'll be talking about hashing. Hashing is a data structure that uses a hash table, which is just an array, to store and retrieve a key value pair. This is the data, and it does this by using a mathematical function. Now, there are many different hashing techniques because of collisions, and I'll talk more about collisions when we get there, but in this video, I'll only be talking about mod hashing, and these are the different types. So direct hashing, double hashing, separate chaining, linear probing, and quadratic probing. Now, there are three functions for hashing: insert, search, and remove. And as for the time complexity, the best is constant and its worst is linear, and I'll go more over that once we get there. So the first technique that we're going to go through is direct hashing. This is where our number that we want to insert, we're going to divide it by the table size and get its remainder. So we can just simply do that by doing x mod 10. So let's do that. So 7 modulo 10 is 7. So we're going to insert 7 at index 7. 79 mod 10, that is 9. So we're going to insert 79 at index 9. 10 mod 10, that's 0. 104 mod 10, that's 4. 57 mod 10, that's 7. Now here, this is considered a collision because we already have a value at that index that we want to insert at. So that's what a collision is. And the different techniques handle collisions differently. For direct hashing, it handles collisions by completely deleting what's at that index and instead replacing it with what we're now inserting, which in this case it's 57. So then we want to insert 44, so 44 mod 10, that's 4. This is another collision because we already have something there. So we're going to completely replace it with 44. So this is why the time complexity is constant, because when we insert, we don't have to traverse through, we can just insert directly. As for search, let's say we're looking for a non-existent, which is like 66 or whatever. This is our key, right? If we're searching for 66, we're not going to traverse through the array. We're just going to find the index by using our hash function. So we're going to hash 66 mod 10, that's 6. And as you can see, at 6 there's nothing, so this is going to return false. The same would be true if, like, let's say our key value is 57, right? So 57 mod 10, that's 7. So at 7 there is a value, so this would return true. So that's why the search is also constant, because you're not traversing, you're going directly to that index. Remove, the same thing. So this is the code for it, where you're going to find the index by using your function, and at that index you're going to place your value. For search, the exact same process. You're going to find your index by using your function, and at that index in the table, if the value is the same, we're going to return true, else we're going to return false. Removing, again, same process. Find your index, and then if at that index in the table is our value that we want to remove, we're going to say -1. This is with the assumption that we already have an array filled with -1s initialized. So at that index, we're going to place it back to -1. So that's direct hashing. So the good thing about direct hashing is that its time complexity is always constant, which makes it super fast. However, let's say you want to save the data that's in the array. Well, this is not good because that data is being overwritten. As for the linear probing technique, the way it handles collision is by placing it at the next available index. And it does this by using this function. So let's start. So we want to insert 57 modulo 10, and we have this iterator. So the first iteration will be 0 modulo 10. That's just 7. As you can see, this is just essentially direct hashing on the first iteration. If there's no collisions, well, that's great. We can just insert it into the table. If there is a collision, as you can see, there is a collision, then we go on to the next. So that would be 57 modulo 10 plus 1 modulo 10, and that's 8. So there's nothing at 8, so we can insert 57 at 8. We want to insert 88, so 88 mod 10, that's 8. We see there's a collision because something is at 8, so we'll do 88 mod 10 plus 1 mod 10, so that's 9. There's a collision, so we go 88 mod 10 plus 2 modulo 10, that's 10. In this case it would be 0. So that's a collision. Then we do 88 mod 10 plus 3 modulo 10, that's 1. There's nothing at 1, so we would place 88 right here. We want to insert 2, so 2 mod 10, that's 2. We see nothing at 2, index 2. So that's linear probing. So as you can see, I was doing this pretty fast. So the reason why is that you don't even have to bother doing all of this. you can just do, let's say we want to insert 57, it's going to be the next one over. We want to insert 88. Well, at 88, index 8, it's taken, 9 is taken, 0 is taken, 1 is not. So I'll insert 88 here, and then 2. That's it. So this is the code for insert. This is with the assumption that our empty slots in the table are -1. So we're going to have an index, and for the collisions, we're going to have an iterator. So we're going to have a for loop, where in it, we're going to initialize the index to our hash function. And if at that index in the table, it's considered empty, we are going to place at that index our value. And we're going to go ahead and break. So this is our search, where again, the exact same process, we're going to have our index, we're going to iterate, and if we're going to set our index, and if our key value at that index in the table is the exact same, we're going to return true. Once it goes through each iteration through the table, it's going to return false if our key was never at that index. So for remove, again, we're going to set our index, have a for loop for our iterations, set our index to our hash function, and then if at that index in the table is the same as the key, well, at that index in the table, we're going to set it back to -1, and we're going to break. That's it. So the time complexity is O of 1, because when we insert, or search, or remove, and there's no collision at all, well, that's just going through it once, so that's constant. As for, let's say we have multiple collisions, well, that's O of n. And the good thing about linear probing is that, yeah, it's going to save our data. However, this is more for like bigger arrays, but it's going to cause clustering. As you see here, we even have it, where there are going to be spaces in the array that are empty and spaces that are clustered together. As for quadratic probing, it's literally the exact same thing as linear probing. However, our iterator is squared. So let's insert 57. 57 modulo 10 is 7. That's a collision. So we're going to go to the next I, which is 57 mod 10 plus 1 squared, that's 1. Mod 10, that's going to be 8. Because on the first, it would just be like linear, right? So that's 8. So 8 is not taken, so we'll place 57 here. Then we want to insert 60. So 60 mod 10, that's 0. We see that there's a collision. So we're going to do 60 mod 10 plus 1 squared, which is just 1, mod 10. That's going to be 1. We see that that's a collision. So then we do 60 mod 10 plus, so 2 squared, which is 4, mod 10. So this is 4 plus 0, that's 4, mod 10, that's 4. So at 4, we see that's another collision. So then we do 60 mod 10 plus 3 squared, that's 9, mod 10. So this is 0 plus 9, 9, mod 10, that's 9. Oh my gosh, that's another collision. So then we're going to do 60 mod 10 plus 4 squared, that's 16, mod 10. So 16 plus 0 mod 10, that's going to be 6. We see finally, oh my gosh, so that's free. So we place 60 at index 6. So then we want to insert 88. So 88 mod 10, that's 8. We see that that's a collision. So 88 mod 10 plus 1 squared, mod 10, that's 9. That's a collision. So 88 mod 10 plus 2 squared, that's 4. So mod 10. So 4 plus 8, 8, 9, 10, and 12, that's 12. Mod 10, that's 2. So 2 is free, so we'll put 88 here. And then we want to insert 3. So 3 mod 10, that's 3. That's free, so place 3. Now, I do not want to do all that, so just really quickly, to not write all of that, you can just take your index. So 7 plus, in this case, 1 squared, that's just 8. So we can place it at 8, so 57. For 60, at 0, so 0 plus 1, that's 1, that's a collision. So we're going to do 0 plus 2 squared, so that's 4. So that's a collision. I can do 0 plus 3 squared, that's 9. That's a collision. So I can do 0 plus 4 squared, that's 16. I'm going to mod again. That's 6. So that's not a collision. So 60. 88. So 8 plus 1, 9. That's taken. 8 plus 2 squared, that's 4. 8, 19, and 12. That's 12. Mod 10. That's 2. It's not taken. So 88 here, and then, yeah, 3. So that's a little faster. So that's how you do quadratic probing. And for the code, that's just going to essentially be the exact same code we did for linear probing, but the hash function, the index, you're just going to multiply it by itself. That's literally the only difference. So the good thing about quadratic probing compared to linear probing is that it's much faster and it causes less clustering. Then we have double hashing, where we have two functions. This one's just basically direct, and this one is going to use a prime number that is less than the table size. So this right here is just both of the functions combined, and then this is what we're going to use for the code. So I'm going to start by doing both of them combined, and then an easier route is just doing them separately. So I want to insert 57. So I'm going to do 57 modulo 10, that's 7, so that's a collision. So then I'm going to go to the next iteration, 57 modulo 10 plus 1 times the next function, which is 7 minus 57 modulo 7, and all that together by modulo 10. Cool. So this right here, this is 7 plus 1 times, so this is 1 minus 7, so that's 6, all of that by modulo 10, so 6 plus 7 is 13, modulo 10, that's 3, so that's free, so 57 goes here. Then we're going to do 24, so 24 modulo 10, that's 4, that there's a collision, so we're going to do 20, we're going to do all of this. I'm just going to copy this because I don't want to write this. So we're going to do 24 modulo 10, so that's 4, plus I times 24 modulo 7, that's 3, 7 minus 3, that's 4. So 4 plus 4 is 8, modulo 10 is 8. So there's a collision. So then we're going to do this again, and instead this will be 2. So this is 4 plus 2 times 4, and that's 8, that's 12. Modulo 10, that's 2. We see that that's empty, so 24 goes here. And then we're going to do 22. So this is 2 plus 1 times 22 modulo 7, that's 1. 7 minus 1 is 6. Modulo 10. So 6, 7, 8, that's 8. So then again, and the next iteration is 2. So this is 2 plus 2 times 6. So this is 12, 11, 12, 13, 14, 14 modulo 10, that is 4. We see that there's a collision, but now this is 3, so this is 2 plus 3 times 6, that's 18, 19, 20, modulo 10, that's 0. We see that's a collision, so we're going to change this to 4, so 4 times 6 plus 2, so this is 24, 25, 26, modulo 10, that is 6. And finally, that's not a collision, so we're going to include 22 at 6. And then we want to insert 55, so that's just 55 modulo 10 is 5, so 55. So that's it. So I don't know about you, but that took like way too long. So let's just do these separately, and it honestly turns out much faster. So we can do h of 1 of x, and then we can do h of 2 of x. So we're going to put all of them together, so 57, 24, 22, and 55. And we know that 57 mod 10 is 7, for 24 it's 4, for 2, and then 5. And then we're going to apply the second function, so 7 minus 57 modulo 7. 57 modulo 7, that's 1, minus 7 is just 6. 24 mod 7, that's 3. We're going to subtract by 7, so that's 4. 2 mod 7, and subtracting by 7, this is just 1, so this is 6. 55 mod 7, that's just 6. Subtract by 7, that's 1. So here, now we're just going to work by iterating. So we're going to take the first one, so 7, plus the second iteration, because we know that the first iteration, well, I'm just going to do it, so it would be 0, right? Times the second hash function. So this is the first iteration, and this is a collision. And then we're going to go on to the second iteration, 7 plus 1 times 6. So just to make sure, yeah, from the first hash function and from the second hash function. Okay, so then this is 13, and since this is greater than 10, I'm going to mod it again, so this is 3, and we can go ahead and place 57 at 3. So then we're going to do 24, so that's going to be, we're going to get this 4, so 4 plus the first iteration times the second hash function, so that's just going to be 4, that's a collision. So then we're going to take 4 plus the second iteration times 4. That's 8. That's a collision. 4 plus the third iteration times 4. So this is 8, 9, 10, 12. So modulo 10, that's 2. And we see that that's free. So we're going to put 24 here. We want to insert 22. So we're going to take 2 plus 0 times 6. So that's 2. That's a collision. So 2 plus 1 times 6. That's 8. That's a collision. So 2 plus 2 times 6. That's 14, which is 4. That's a collision. So 2 plus 3 times 6. That's 20. Modulo 10. That's 0. So that's a collision. And then 2 plus 4 times 6. That's 26. Modulo 10. That's 6. So that's where we place it. 22. And then 55 is just 5 plus 0 times 1. We know it's 5. So we place 55 at 5. And that's it. So for the code, it's literally the exact same thing as linear and quadratic probing. In regards to, you have your iteration, you have your index. The only difference is that the index will use this formula, where you're going to call this hash1 function, where it's going to just return direct hashing, and then you're going to have this hash function that's going to do your prime thing, right? So yeah, so it's going to, yeah, it's literally the same thing. The same for search, just different index. And yeah, that's it. So double hashing is literally the same thing in regards to quadratic probing compared to linear probing, where it's less clustering and it's much faster than linear probing. Okay, so this is the last one, I promise. This is called separate chaining, and it's going to use the same function as a direct hashing function. However, the array won't hold values, it's going to hold linked lists. So if we want to insert 57, we know that there's a collision, and instead of overriding like direct hashing, we're just going to link it to the linked list. Then we want to insert 4, so we see that there's a collision, so we're going to link it. We want to insert 107, there's a collision, so we're going to link it again. We want to insert 77, there's a collision, so we're going to link it again. And lastly, we want to insert 22. We see that 22, there's no collision, so we're just going to add it. And that's it. As for the code, since we are dealing with linked lists, we're going to need a node struct, and for when we want to insert, our index is just essentially going to be direct hashing, and we're going to create a new node. And if at that index in the table, assuming that the table is filled with node pointers and they're all initialized to null, at that index, we're going to insert the new node if, again, if it's null pointer. If it's not, it's already filled, well, we're just going to iterate through this index to insert. So we're going to have a current pointer at that index, and we're just going to iterate till we get to the end. In this case, it would be this one, and we would just place the new node after that. For the search function, we're going to get our index by doing direct hashing, and then we're going to traverse at that index in the table to search for. So once we get our index, we're going to traverse through that index, and if our value is found, let's say we're looking for 107, if when we're traversing we find 107, we're going to return true. If we don't, we're going to return false. So for remove, I'm going to have a call for search to see if it's in the table or not. If it's not in the table, I don't want to remove anything, so I'm just going to return. And then I'm going to get my index, and then I want to start at the head at that index, and then I just want to hold a tracker. So this is the iteration that we're going to traverse through the linked list at that index, right? And so if our node that's going to be removed is found, let's say the node is at the head, well, then we want to point the head to the next node. But if it's not, let's say the node is in the middle or the end, we just want to bypass the current node, and then we just want to free the memory of the node, and then we want to exit. So then for the iteration here, it's this part right here, where we just want to move the previous to current, and then move current to the next node. And that's it. So lastly, we see that when we're just inserting at the beginning, just once, it's constant time. But as you can see, once we start like inserting a bunch at the same index, it starts to become oven. And that's it. Thanks for watching.